Welcome back to G Fun Facts Online. When we envision the cosmos, we often imagine galaxies as majestic, isolated islands of stars floating serenely through an empty, frictionless vacuum. However, the universe is far more dynamic and hostile than this quiet picture suggests. In the dense, chaotic environments of massive galaxy clusters, space is anything but empty. These colossal gravitational metropolises, built from hundreds or thousands of galaxies bound together by immense halos of dark matter, are filled with a superheated plasma known as the intra-cluster medium. When a gas-rich spiral galaxy gets pulled into the gravitational well of one of these enormous clusters, it does not simply glide in. Instead, it plunges directly into a scorching cosmic headwind. The resulting aerodynamic friction is so intense that it violently reshapes the galaxy, blowing its star-forming gas outward to create sweeping, luminescent tentacles. Astronomers call these extraordinary objects jellyfish galaxies, and they are currently providing some of the most profound insights into how galaxies live, evolve, and ultimately die. To understand the sheer scale of the violence occurring within a jellyfish galaxy, we must first look at the precise physical mechanism driving its transformation: RAM pressure stripping. First theorized in 1972 by astronomers James Gunn and J. Richard Gott, RAM pressure is the drag force exerted on a physical body as it moves through a fluid medium. While the gas of the intracluster medium is highly diffuse by human standards, the astronomical velocities at play make its impact completely devastating. When a spiral galaxy falls toward the center of a massive cluster, it can easily reach blinding speeds of several million miles per hour. As it plows through the intracluster medium, which is heated to staggering temperatures of up to 100 million Kelvin, the galaxy experiences an intense aerodynamic pressure. To visualize this sheer force, researchers often use the analogy of a dog sticking its head out of the window of a fast-moving car on the highway. The sheer force of the oncoming wind blows the dog's fur backward. In our cosmic scenario, the fur is the galaxy's interstellar medium, which consists of the vast reserves of cold hydrogen gas and cosmic dust that serve as the vital fuel for the birth of new stars. The RAM pressure acts as a powerful headwind that overcomes the gravitational pull of the galaxy's disk, physically ripping the cold gas away and stretching it far out into the darkness to form trailing tails. Crucially, the stars that have already formed within the galaxy, along with its invisible dark matter halo, are generally far too compact and massive to be affected by this aerodynamic drag. So, the stars remain gravitationally bound to the disk, continuing their regular rotation as if absolutely nothing were wrong, even as the very lifeblood of their galaxy is siphoned away into deep space. The most famous and visually arresting archetype of this phenomenon is ESO 137001, a barred spiral galaxy located approximately 220 million light-years away in the Norma cluster, also known as Abell 3627. Discovered in 2005 by astronomer Ming Sun, ESO 137001 is hurtling toward the cluster's center at an astonishing speed of 1900 kilometers per second, which translates to nearly 4.5 million miles per hour. As it crashes through the Norma cluster's searing 180 million degree Fahrenheit intracluster medium, the intense RAM pressure stripping has drawn out a spectacular tail of gas that spans over 260,000 light-years. To put that into perspective, that is more than double the entire diameter of our own Milky Way galaxy. Observations taken from the Hubble Space Telescope and the Chandra X-ray Observatory reveal ESO 137001 as a cosmic dandelion caught in a hurricane, shedding its seeds into the void. But the stripped gas does not simply vanish into the background heat of the cluster. Instead, it forms a highly complex, multi-phase wake. Dense knots of cold molecular gas actually manage to survive within the sprawling tail, triggering intense bursts of what astronomers call extraplanar star formation. These stellar nurseries, existing entirely outside the galaxy itself, produce brilliant clusters of young, massive blue stars, lending the galaxy its glowing, jellyfish-like tentacles. For years, the survival of this cold, star-forming gas in an environment surrounded by 100 million degree plasma completely puzzled astrophysicists. How does the stripped interstellar medium avoid instantaneous evaporation in that kind of inferno? Recent multi-wavelength studies, utilizing powerful observational arrays like the Atacama Large Millimeter Submillimeter Array and the Carl G. Jansky Very Large Array, have pointed to a fascinating protective mechanism known as magnetic draping. As the galaxy moves rapidly through the magnetized plasma of the intracluster medium, the cluster's magnetic field lines actually catch and drape themselves perfectly over the galaxy's stripped tail. This magnetic sheath acts as an incredible insulating barrier, suppressing thermal conduction and actively shielding the cold, dense clouds of molecular gas from the surrounding inferno. Tucked safely within this protective cocoon, the gas is able to cool, condense, and collapse under its own gravity to birth new stars far beyond the galactic disk. While ESO 137001 serves as a phenomenal local textbook example, modern observatories are continually pushing the boundaries of when and where these cosmic leviathans can exist. In February 2026, a groundbreaking discovery was announced using data from the James Webb Space Telescope that fundamentally altered our timeline of galactic evolution. Deep within the Cosmic Evolution Survey field, a team of researchers led by Dr. Ian Roberts from the University of Waterloo identified a previously undocumented jellyfish galaxy, officially designated as Cosmos 2020 to 635,829. What makes this galaxy truly extraordinary is its extreme distance and age. It possesses a redshift of Z equals 1.156, meaning its light traveled for 8.5 billion years just to reach the mirrors of the James Webb Space Telescope. We are observing this galaxy exactly as it existed when the universe was only about 5.3 billion years old. Prior to this massive discovery, astrophysicists widely believed that the early proto-clusters of the young universe had simply not yet accumulated a sufficiently dense intracluster medium to trigger such violent ram pressure stripping. It was highly assumed that jellyfish galaxies were strictly a feature of a more mature, modern universe. The discovery of Cosmos 2020 to 635,829, complete with its massive trailing tendrils of gas and clear evidence of extraplanar star formation, definitively proves that severe environmental quenching and ram pressure stripping were already actively shaping the evolution of galaxies during the cosmos' turbulent adolescence. To comprehensively map out the intricate physics of these transformations, astronomers launched the GASP survey, which stands for Gas Stripping Phenomena in Galaxies with MUSE. Coordinated by Bianca Maria Poggianti of the National Institute for Astrophysics in Italy, this ambitious project utilized the multi-unit spectroscopic explorer instrument on the European Southern Observatory's Very Large Telescope. By observing over 100 different jellyfish candidates across a variety of cosmic environments, the GASP team has successfully painted an incredibly detailed picture of the baryonic cycle, which is the continuous exchange of matter between a galaxy and its environment. One of the most surprising revelations to emerge from the GASP survey is the highly unexpected link between ram pressure stripping and active galactic nuclei. At the heart of nearly every large galaxy lies a supermassive black hole, but in most galaxies, these behemoths are dormant. However, the GASP team discovered that an unusually high number of jellyfish galaxies actually host highly active, ravenously feeding black holes. It turns out that while ram pressure acts primarily to push gas out of the galaxy's outer disk, the chaotic, asymmetric forces at play can also cause some gas to drastically lose its angular momentum. Without that rotational momentum to keep it in orbit, the gas funnels directly inward toward the galactic core. This sudden influx of material effectively awakens the supermassive black hole, which rapidly accretes the gas and unleashes absolutely massive amounts of energy. Galaxies like JW100, a prime subject of the GASP survey, represent a stunning cosmic laboratory of these concurrent extremes. While its outer edges are being violently stripped away to form spectacular X-ray emitting tails, its very core is ablaze with massive active galactic nuclei activity. The GASP survey also shed vital light on the kinematic strangeness of the stripped gas. Deep observations revealed that the gas plumes swept out into space actually continue to rotate with the exact same velocity signature as the parent galaxy they left behind. This remarkable preservation of angular momentum far out into the intergalactic void serves as undeniable kinematic proof that aerodynamic drag from the cluster gas, and not tidal gravitational forces from a passing galaxy, is the primary culprit behind the stripping. Furthermore, Advanced cosmological supercomputer simulations like Illustris TNG-50 are helping astronomers understand the long-term fate of these galaxies through large-scale citizen science projects like fishing for jellyfish. These hydrodynamic simulations trace the entire lifespan of satellite galaxies falling into massive halos. They brilliantly reveal that the ram pressure stripping process is not instantaneous at all. Instead, it can be a protracted, slow agony lasting anywhere from 1.5 to 8 billion years, with the most intense period of gas loss occurring entirely within the first billion years of the galaxy's initial infall into the cluster. Remarkably, these advanced simulations show that jellyfish galaxies are actually a massive source of cold gas accretion for the cluster itself, depositing billions of solar masses of cold gas into the host halo and drastically enriching the intergalactic space with heavy elements forged deep in the galaxy's stellar furnaces. Ultimately, the majestic, glowing tentacles of a jellyfish galaxy are a grim signal of its impending doom. The spectacular bursts of blue star formation seen in the tails are a final, defiant fireworks display before the end. As the ram pressure relentlessly removes the cold atomic and molecular gas, the galaxy is entirely deprived of the raw materials needed to sustain its stellar populations. Once the gas is completely stripped, star formation within the galaxy's disk grinds to a permanent halt, a bleak process known as quenching. The galaxy forcefully transitions from a vibrant, blue, star-forming spiral into what is known as a red and dead lenticular galaxy. It retains its central disk structure but completely lacks the sweeping spiral arms and the luminous blue glow of young stars. The GASP project has directly observed this precise morphological metamorphosis taking place, noting how the aggressive stripping of gas can cause beautiful spiral arms to literally unwind, leaving behind a barren lenticular husk drifting silently through the cluster. Jellyfish galaxies represent a highly critical, transitional phase in the grand story of cosmic evolution. They act as unparalleled astrophysical laboratories that allow us to directly witness the wildly complex interplay of gravity, hydrodynamics, magnetic fields, and thermodynamics on a scale spanning millions of light-years. From the local universe's ESO 137001 bleeding its gas into the Norma cluster, to the James Webb Space Telescope's Ancient Cosmos 2020 to 635,829, drastically challenging our timelines of the early cosmos. These remarkable objects powerfully demonstrate that galaxy clusters are not peaceful cosmic retirement homes. They are wildly turbulent, deeply unforgiving environments where galaxies are dramatically and violently reshaped. Through the continued synthesis of deep space observation and advanced simulation, the ongoing study of jellyfish galaxies promises to further unravel the complex, violent, and incredibly beautiful processes that continuously dictate the life and death of galaxies within the vast cosmic ocean.